will solve the flow in the unit cell that we started introducing last time, and I just figured out that if I give you a worksheet, you will be more active during class. Your brains will be more active than if you're just copying from what I'm writing on the screen. So basically, what we're looking into a sphere, okay, that is flow around the sphere, but this time we're interested in a sphere that is falling down through the liquid at a uniform velocity u. But in order to actually analyze the problem, we will attach ourselves to the sphere. Okay? So that's going to be the biggest stumbling point in this problem, are actually figuring out what the boundary conditions should be for the problem. So basically we will encase this sphere. Let's say that the sphere is of radius a, such as drawn on your worksheets, and we will encase it in a slightly larger sphere that has radius b. Okay? And we will basically, that's where all of the flow and everything is happening within that, what we call unit cell. Okay? So before we actually start looking into the boundary conditions, I can put this ball around, it's fun to play with. But basically what we will do is we will solve for the flow around this one sphere. But what we are ultimately interested in is flow around a whole collection of spheres. This is called close packing of 4 spheres. And essentially, in porous media, basically a lot in terms of permeability is constrained by these what are called throats. So if you imagine centers of these 4 spheres to be a tetrahedron, okay? So they form a tetrahedron. Each side of the tetrahedron, okay, you can look what remains of that side when you remove the spheres, and that's sort of the tightest portion of this medium. Okay? So basically what remains, this is one side of the tetrahedron. The throat is this empty space in between the spheres. Okay? So that is the tightest portion of a tight packing of equal spheres. Okay? And so-called wide portions of the medium are actually the pores, which is inside in this, so basically pore space in between the 4 of these spheres. So this pore is connected to other pores via these tight connections, which are converging, diverging geometries, and the tightest part is actually on the side of this tetrahedron geometrically. And basically those are your tight spots, and your wide spots are these spheres that are in between the 4. So I will send this if you just want to enjoy a spatial configuration. And then essentially you will find some of the, so basically this is a sphere packing. This is a 3D printout of a sphere packing, actually one that has been measured experimentally. And if you need those X, Y, Z's of these spheres, I can give them to you. This has been a little beaten, so some of the spheres have chipped off, but it actually enables you to see inside. Okay? And you can see that some of these tetrahedra, some of them are close like this, but some of them will be something like this. Okay? Or like this, or something like that. So 4 closest spheres basically form a pore, and that pore could be, the tightest one is this, but there could be slightly different configurations, of course. Okay? So you can enjoy these. But what we are actually after, so we will first solve unit cell problem around one sphere. Okay? I will pack it into a unit cell, and then I will kind of squish all those unit cells into a packing like this, and basically find a relationship between A, B, and porosity. So first review that part in number 1. Let's review that. I basically outlined it last time, so please review that, and then we will continue on with solving. So first focus on number 1. And you can, in the meantime, also enjoy these toys, which unfortunately are not on the video. Too bad. But that's... So basically, we're working through the worksheet, and first we are reviewing what is the relationship between porosity A and B. And if you're done with that, you can proceed reading with the rest of the worksheet. Whatever it is that you do not be bored. I live close to a park that has a tennis center, so you just need to walk around the playgrounds and collect the balls. I collect them for my dog. Plenty of tennis balls for my at my disposal for research purposes. Because there are always people who hit the ball across the fence and are lazy to go pick it up. If anybody else wants to. Did you work through number 1? So number 1 is just a review of what we did last time. So these are my 2 spheres. Volume of each is related to its radius in something that we learned in elementary school. And then if I look at the solid fraction that I have within this unit cell, it's basically volume of the smaller sphere divided by volume of the unit cell. But that's also 1 minus porosity. So basically that gives me a relationship between A, B, and porosity. And then we actually did this last time for 0.5. If my phi is 0.5, then I get that B over A is 1.26. So it's not much larger than A itself. Okay. Now I pack all, and this assumes that I really tightly packed all of those unit spheres within the volume of a sphere packing such as the one that is floating around printed in 3D. All right, now let's move on to number 2. So I will leave you first to walk through it yourselves. Basically, we have 3 assumptions, or rather, I'll talk you through it and then you will have to write it down as formulas. So basically, we assume that sphere, the equivalent of sphere falling down in liquid is actually fluid moving at the velocity u upwards, okay? And upwards, downwards, as long as we assume one thing consistently, it's the same thing. So basically, we actually have a constant at the sphere boundary, okay? if I'm actually in this system that is moving with the sphere, the system is moving with the constant velocity. So what we would normally say, okay, my viscous fluid is attaching to the sphere, right? It's sticking to the sphere and its velocity is 0. In this moving coordinate system, it's not going to be 0, it's going to be moving with that velocity. Okay? So basically I just need to translate the coordinate systems. So how would you, so basically my VR and V theta on the sphere boundary, which is R is equal to A, have to be this velocity translated to spherical coordinate system. Let's calculate that. So basically my velocity is given in z direction, right? Which is XYZ coordinate system. I gotta translate that . I'll stop the movie.